So we'll continue with the introduction to absorption spectroscopy. So last class we were discussing about the electronic transitions. We will continue from there. I had explained about the absorption with different types of radiations having different energies and what kind of transitions are brought about. In case of IR, it is vibrational transitions. In case of visible, it is electronic transitions involving lower energy compared to UV, which involves higher energy, again electronic transitions, because there is a transition from the ground state to the higher or these higher excited state. In case of visible, it is usually from the ground state to the next higher excited state. We also saw about relaxation, because absorption and excitation of a molecule always makes the molecule unstable. So it tends to give off the excess energy, be it molecule or electrons or atoms. They become unstable when they gain the excess energy. So this energy will be given out by the entity. So that process is called relaxation. You could have non-radiative relaxation, or you could have relaxation with radiations being emitted. So this also we completed last class. This is non-radiative relaxation. That means the molecule, electron, atom or ion, it loses the excess energy and returns to the ground state, that is lowest energy state, without emitting any radiations. This could be because of collisional deactivation, which may result in transfer of the excess energy to the surrounding solvent molecules also, which is the most commonly encountered phenomena of relaxation in solutions. It may also involve vibrational relaxations. That means small losses of energy as the molecule reaches the lowest vibrational level of an excited state, because it is only from this that emission can take place, or radiation can be emitted. But if uh, for a particular molecule, if it is not a fluorescent molecule, then radiation will not be emitted. Instead, there will be something called an external conversion, which you study in detail in fluorimetry. So those are non-radiative methods of relaxation. We completed this also last class. Now we go to the next one, that is emission. Sometimes absorption and excitation may result in emission also. So there could be emission of radiation resulting in release of excess energy that was absorbed. So that is fluorescence. So this type of emission always takes place from the lowest vibrational level of any excited state. So here you can see E0 at vibrational level 0. That is the lowest vibrational level of E0. From here, there could be emission of slightly different wavelengths. So here you can see this wavelength is longer compared to this, because this is the energy axis. This energy is less, this is slightly more, still more, still more, and still more. So progressively the wavelength becomes shorter as you go from left to right here. Similarly from this, because if the excitation has taken place to the even electronic state, then there will be vibrational relaxations to the lowest vibrational level of E1, and from which there could be radiation being emitted. That is, fluorescence may be emitted. Now, when this fluorescence is emitted, it could vary over a small range of wavelengths or energies, because it could emit this wavelength or this energy, or slightly higher, or still higher, or still higher, and still higher. So each of these, since they differ in energy, they also differ in wavelength. in the opposite way. That means if this energy is the least, then this will be the longest wavelength and this will be the shortest wavelength. So this is about how absorption is followed by relaxation, which could be non-radiative or it could be radiative. That is, fluorescence or phosphorescence may take place. Now this is another representation of the same thing, just to make it a little more clear, and how you get a chromatogram. So here you get the chromatogram. See, this is the intensity and intensity axis versus the, say, the wavelength axis. Now you can see in this first one, this is increasing energy. So S0 here has been used to represent the ground state. S1 is the first excited state and S2 is the second excited state of greater energy than S1. If you have these wavelengths corresponding to, say, the violet color shown here, then you can get excitations to the S2. That means these wavelengths are much shorter than these wavelengths because the energy involved in the absorption is much greater. Energy is so much, S2 minus S0, a larger energy compared to S1 minus S0. So the blue ones represent a smaller energy transition. Now both these anyway will result in absorptions, and so you can get an absorption spectrum of intensity versus wavelength, shorter wavelength first and then the longer wavelength. So you get two peaks because of absorptions occurring. Next, it is followed by vibrational relaxation and internal conversion. Here you can also see the time taken for each of this. Absorption occurs in 10 raised to minus 15 seconds after irradiation. Vibrational relaxation and internal conversion, these are non-radiative relaxations. They take place within 10 raised to minus 12 seconds. Then emissions, fluorescence and phosphorescence, they take little longer than this one. So fluorescence takes about 10 raised to minus 9 seconds and phosphorescence is greater than 10 raised to minus 3 seconds. So suppose vibrational relaxation has occurred, then you don't get the fluorescence and phosphorescence spectra. Suppose it is resulting in radiative relaxation, that is fluorescence, then you will see from S1, all these vibrational levels, it is going to come down to the lowest vibrational level from which fluorescence will be emitted. Again, you will see that it will form a peak like this, and this is called the fluorescence peak. It is intensity of fluorescence versus the wavelength. Now here what is shown is this is phosphorescence, because this involves one more conversion over overlappings, that's called intersystem crossing. Again, this you will study in detail in fluorimetry. But when it crosses over to another energy state T1, it's a triplet state, then it will undergo further vibrational relaxations, reach the lowest vibrational level of T1, and then it will emit radiations. This emitted radiation will be called phosphorescence because it's a transition from the triplet state to the ground singlet state. So this is another representation. Hope it is clear now about how these transitions take place for absorption and excitation, and then followed by relaxation, non-radiative relaxation, and radiative relaxation. Now each electronic level, now we were talking about electronic levels only. Now we'll see a little more in depth. Each electronic level is comprised of a number of vibrational levels. Each vibrational level is comprised of a number of rotational levels, and very little energy is required for pure rotational transitions. This occurs in the far IR and microwave regions, and they also result in line spectra. I will show you pictures of all this. Very little energy is required for pure rotational transitions, and they result in line spectra. Also, atomic spectra are line spectra. More energy is required for vibrational transitions. Only vibrational rotational transitions are possible. You cannot have pure vibrational transitions. It will always be vibrational rotational transitions, and this occurs in the IR region. This leads to narrow band spectra. So what is narrow band spectra? I will show you a picture of that also. And finally, you have electronic transitions. This occurs in the UV visible regions. We have been so far seeing about electronic transitions only. This occurs in UV visible regions, and this always results in broadband spectra. So this is a picture of continuous spectrum, an absorption spectrum, and an emission spectrum. This is line spectrum. So here you can see the lines. In a continuous spectrum, all the wavelengths are being emitted. So suppose it's a visible light, all the colors are being emitted. Okay. Now in an absorption spectrum, you will see the same continuum as in this, but the sample is absorbing at certain wavelengths. So at those wavelengths, you will get dark lines. So absorption spectrum gives dark lines at the wavelengths at which the sample absorbs. But in an emission spectrum, you will see a dark background, and the same substance would give you colored light. Because this is visible region, it will be colored. So colored light bands are seen. So these are lines that are obtained with colors. So you can see it is green color here. So at the same wavelength in an emission spectrum, you will see green light. Here it's violet. Sorry, it's almost blue. Here it is violet color. This is orange. So you get an orange line. So in an emission spectrum, we'll always look with a dark background and the various lines which have been emitted with the respective colors if it is visible light. And here you will, in an absorption spectrum, you will see a lighted background with dark lines at wavelengths in which there is absorption. That is the difference between absorption and emission spectrum. Now also narrow band spectra and broadband. Now line spectra are obtained only in the far infrared and microwave regions. Other than that, atomic spectra are line spectra. Molecular spectra, on the other hand, are band spectra. Now, this is a narrow band spectrum of salicylic acid, and this is a broadband spectrum of salicylic acid. Now, this type of narrow band spectrum you get in infrared region, and therefore this is an infrared spectrum. What you see here is it is inverted. The peaks are inverted because we have used transmittance here. Transmittance and absorbance will be reciprocals, logarithmic reciprocals of each other. That is why here the peaks are inverted. If you have percentage transmittance, this will be into 100 values, but the peaks will look the same. What I want you to look at is the peak widths are very small here, and you see a number of peaks also. This happens in infrared spectrum. You see a number of peaks because each group in the molecule will give rise to its own peak in the infrared region. Here, on the other hand, you see a broadband spectrum. This is taking place in the UV visible region. A broadband is obtained because the chromophore in the molecule as a whole, its presence in the molecule, its environment in the molecule together gives one spectrum. So you get a broadband spectrum, and you see there will be very few peaks, 1, 2, or maximum 3 peaks. You will not see so many peaks in a UV spectrum. So this is a broadband spectrum. This is a narrowband spectrum. Another example, this is for benzene. So you have infrared spectrum of benzene here, and here you have the UV visible spectrum for benzene. So you will see a broadband spectrum for benzene in the UV visible region, whereas you see narrow bands in the infrared spectrum of benzene. Coming back to electronic vibrational rotational transitions. I also mentioned last class there is something called translational energy also. But in spectroscopy, we will be concerned with only electronic, vibrational, and rotational. These are the internal energies. Now, see, this is how they are related. This is just a pictorial representation of that. This is the energy axis. So this electronic energy level has lower energy. This is slightly higher, and still higher. Now, in this one electronic energy level, if we magnify this, then you will see a number of each of these lines corresponds to one of these. So this corresponds to this, the next line to this, like that. So this is an expanded view of these four. Each of these four now can be seen as having a number of lines again. So these lines represent, these first lines, these represent the vibrational levels in an electronic state. Now, in these are the number of vibrational levels, and each of these lines represent rotational levels in that vibrational energy state. So each vibrational energy state has a number of rotational levels. Again, magnifying this part, you will see each one being split into a number of lines. And each of these lines represent one translational energy level. So this is quantum mechanics, which demands discrete energy levels. So I hope it is now clear what is vibrational, what is rotational, and what is electronic energy levels. There's another representation making it more and more clear to you. This is the ground state S0. It's an electronic energy state which has a number of vibrational levels associated with it. Each of these vibrational levels have a number of rotational energy levels associated with it. This is the second electronic energy level. So this is an excited state. This also has a number of vibrational levels of its own, and each vibrational level has a number of rotational levels of its own. So this entire thing is S1, excited electronic energy level. S2 is a second excited electronic energy level, which has also got number of vibrational, and each of them have number of rotational energy levels. So you can have transition from this state, ground state, lowest state, to any of these levels anywhere. If it is within the first ground state itself, then it does not involve electronic transition. In case of UV visible radiations, the energy of the photons is sufficient to cause electronic energy transitions. So definitely it will go to either the first or to the second, depending upon the energy of the photon. It need not go only to the lowest electronic energy vibrational state. It can also go from here to any of the vibrational or rotational states, to any particular to these, not in between the two levels. So suppose now this is one electronic energy level, E0. It has number of vibrational levels, V0, V1. Similarly, this is E1, with electronic energy state with number of vibrational levels V0, V1. You can see V0 has R1, R2, R3. Similarly, V1 also will have R1, R2, R3. Now, if radiation is incident and absorption is occurring, resulting in such a transition, that is V0 to R1 or V0 to R2 or from R1 to R3, all these are pure rotational transitions. They have not changed any vibrational level nor changed any electronic energy level. Hence, they are called pure rotational transitions, and these will result in line spectra. On the other hand, if you see the second one, here you have a transition from V0 to V1R1, V0 to V1R2, and from here V0R1 to V1R3. All these involve vibrational transition because they're crossing into the next vibrational level from V0. They're not within V0. So they all involve vibrational transition. But whenever you can never have a pure vibrational transition, because whenever you have a vibrational transition, it will involve passing number of rotational levels. So number of rotational transitions are involved. And that is why all these rotational transitions are occurring along with a vibrational transition. And hence you cannot get a line spectra in this case. What you will get is narrow band spectra. Each of the narrow bands are comprised of a number of lines corresponding to each of these rotational transitions that it involves. So you get narrow band spectra. This is what happens in IR region. This happens in the far IR and microwave regions. This happens in the IR region. And finally, you come to this where you have a transition from E0 to E1 involving much greater energy. So here it is E0 V0 to E1 V0 R1. This is E0 V0 R1 to E1 V0 R2. All these include, all the three of them include a transition to the next electronic energy level. So it's an electronic transition and it will result in a broadband spectra. So why it becomes a broadband? Because here it will also include a number of vibrational transitions. See, here one, here one. So this is a number of vibrational transitions occurring. And each of these vibrational transitions also have number of rotational transitions involved. That is why you get a broad band spectrum with a number of narrow, which is comprised of a number of narrow peaks within it. Each of the narrow peaks in turn is comprised of a number of closely spaced lines. So which represent rotational narrow peaks, vibrational, and the whole overall is a broadband spectrum which represents electronic transitions. That's why you get a broadband spectrum with electronic transitions in case of UV visible radiations. So in electronic transition, an electron from one molecular orbital moves to another orbital with an increase or decrease in the energy of the molecule. It could involve an increase or decrease. See, I have not told it's an absorption. It's a transition. So when absorption is occurring with an increase in the energy of molecule would be correct. And when relaxation is occurring, then with a decrease in the energy of molecule would be appropriate. So the same thing you can use to tell about absorption and relaxation, but either one of this has to be used. So in absorption, it's an electronic transition, and here an electron from one molecular orbital moves to another orbital with an increase in the energy of the molecule. However, when the molecule is relaxing, that would also be an electronic transition where an electron from one molecular orbital moves to another molecular orbital with a decrease in the energy of molecule. So now we see about combined electronic, vibrational, and rotational transitions. So when a molecule absorbs light having sufficient energy to cause an electronic transition, vibrational and rotational transitions, that is changes in these vibrational and rotational states, can occur as well. I just showed you in the previous slide. The reason why electronic absorption bands are usually very broad is that many different vibrational and rotational levels are available at slightly different energies. Therefore, a molecule can absorb photons with a fairly wide range of energies and still be promoted from the ground electronic state to one particular excited electronic state. That is what I mentioned earlier, that a number of transitions will take place, each resulting in its own spectrum. So rotational all will give lines, vibrational will give small peaks. And what does it mean? If it means that a photon of higher energy is being absorbed. That's what it means. So you get a broadband spectrum. So that's about electronic transitions. Now we'll see the relationship between electronic spectra and molecular structure. So you have different types of electrons: closed shell electrons that are not involved in bonding, covalent single bond electrons, which are called the sigma electrons. You also have paired non-bonding outer shell electrons, which are the n electrons. And finally, you have the electrons in pi orbitals, that is the pi electrons. So these are the four types of electrons. So what are the possible transitions in the UV visible region? Now, these closed shell electrons are not involved, mainly because they require very high energies to undergo a transition, and that high energy is not available with the UV visible radiations. Similarly, covalent single bond electrons are also not involved because they also require more energy for transition than what is possessed by UV visible radiations. Now, the other two, the last two, paired non-bonding outer shell electrons, that's the n electrons, and the pi electrons, can be excited. So the possible transitions in the UV visible region are pi pi star, n pi star, n sigma star. I have put in the order of the probability of these transitions occurring. So pi pi star is the most probable one, n pi star is slightly less, and n sigma star is rarely seen only in certain molecules. So here again, it's the same what I just told you. Probability of pi pi star transitions is greater than n pi star transitions. Since the probability of these is more, you get more intensity absorption bands. Intensity of absorption bands are greater for pi pi star than for n pi star. So the band that you get will be a much bigger band for pi pi star, and a smaller band or height of the band will be smaller for n pi star, as evidenced by the epsilon max values. Epsilon max is a value, it's called the molar absorptivity and the maximum molar absorptivity. For pi pi star transitions is about 1000 to 100,000, whereas for n pi star transitions it is less than 1000. So you can see you can imagine the difference in the peak heights, the one for pi pi star and the one for n pi star. This represents almost the peak height. So what is molar absorptivity? We just saw in the last slide epsilon value. It expresses the relative intensity of an absorption band. You could also say it's a measure of the probability of the electron transition taking place. Greater the probability, greater the relative intensity. And it is proportional to the fraction of radiation absorbed at a given wavelength. So how much is absorbed? So ultimately it depends upon absorption. Greater the absorption, greater the probability, greater the intensity. So to define molar absorptivity, it's the absorption of radiation passing through a 1 molar solution of 1 centimeter depth. It is the absorption of radiation passing through a 1 molar solution of 1 centimeter depth. The thickness will be 1 centimeter. The concentration will be 1 mole per liter. And such a solution, you pass radiation. If you measure the absorbance, it's nothing but molar absorptivity, epsilon value. So relative energies of molecular orbitals. Here you see the energy axis. It increases in the upward direction. You have different orbitals. This is the bonding sigma orbital, bonding pi orbital, non-bonding n orbital, anti-bonding pi star orbital, anti-bonding sigma star orbital. These anti-bonding orbitals are unoccupied orbitals at room temperature with no excitation. These are also the excited states. So these are the normally occupied orbitals. Whenever these electrons are excited, they will undergo a transition to the anti-bonding orbital. So compounds containing only sigma bonds have absorptions only in vacuum ultraviolet. At the most, they can have it only in vacuum ultraviolet, or they go for still more energetic regions, that is extending into the X-ray region. So the sigma bonds, only containing sigma bonds, means they are the saturated compounds. So saturated compounds will not show absorptions in the UV visible region. At the most, it can show absorption in the vacuum ultraviolet region. Vacuum ultraviolet region extends from 5 to 180 nanometers, and UV region starts from 180 to 380 nanometer. Visible region starts from 380 and extends to 780 nanometers. Now these transitions correspond to sigma sigma star. That is why this type of transition does not take place in UV visible regions. Next, you have the pi electrons. The pi electrons can get excited to the pi star antibonding orbital. This energy is possessed by the UV visible region, so this can easily take place. So pi electrons are found in unsaturations. So unsaturated molecules always have pi electrons. And so all the unsaturated molecules will be capable of absorbing UV or visible radiation. Then you have the non-bonding electrons. The non-bonding electrons, or N electrons, can be excited either to the pi star or to the sigma star. The N sigma star transition involves slightly more energy than the pi pi star transition, and definitely more energy than the N pi star transition. So this is commonly seen, but it is seen only in those molecules which have these N electrons. If N electrons are not present, then this transition is not possible. And the number of N electrons will also be very limited, and that's why the probability of this transition is much lower than the pi pi star transitions. N sigma star for some molecules may involve an energy which corresponds to the UV region. So it may take place in UV. Generally, this for most molecules is seen in the vacuum ultraviolet region. For some molecules, it may be seen in the UV region, that is at wavelengths greater than 180 nanometer, 180 to 380. It may occur for certain molecules only. Majority of the molecules will show N sigma star also in the vacuum UV region. So the primary transitions are N pi star and pi pi star, out of which this is the most probable transition in UV visible region. So we'll see each of these in detail. N sigma star transition. Saturated compounds with lone pair of electrons undergo N sigma star transition in addition to sigma sigma star transitions. Since they are saturated compounds, they definitely have sigma electrons. So these sigma electrons can undergo a transition to sigma star anti-bonding orbital, but this cannot take place with the UV visible radiations. On the other hand, N sigma star may take place in the UV visible. So if it takes place, you get a spectrum. Corresponding absorption bands appear at longer wavelengths in near UV region. So this can take place only in very rarely in the near UV, almost never. It is usually in the far UV region, or not usually. That also is quite rarely seen. It is in the vacuum UV more commonly. You have the sigma-sigma star transitions. These transitions can occur in such compounds in which all the electrons are involved in single bonds, and there are no lone pair of electrons. No lone pair of electrons means no n electrons, only sigma electrons. Then it has to be only sigma-sigma star transition. Energy, however, required for sigma-sigma star transition is very large, so the absorption band occurs in the far UV or still beyond, but definitely not in the UV region and in the visible region. So this transition is normally not observed in UV visible region. Next, you have the n-pi star transition. N-pi star transition requires lowest energy due to longer wavelength. So they are forbidden, and corresponding bands are characterized by low molar absorptivity. Epsilon max is less than 100. It is also known as R band. This is the other term used to um, name this n-pi star transition. When you have two bands, one could be an R band, and that R band signifies n-pi star transition. They are further characterized by hypsochromic shift or blue shift observed with an increase in solvent polarity. Now, if you have a band due to n-pi star transition, the shifts in that band due to changes in solvent polarity would be opposite to the shifts observed for pi-pi star transition. Note here that when the solvent polarity is increased, that is, you change from a solvent of lower polarity to a higher polarity, then you will see a shifting of the peak, or the R band shifts to shorter wavelengths. That's a hypsochromic shift or blue shift. We'll see a little later in the following slides. And the last one is the pi-pi star transition. It is due to the promotion of an electron from a bonding pi orbital to an anti-bonding pi star orbital. Energy requirement is between n pi star and n sigma star. So the energy involved will be in between these two. But the extended conjugation and alkyl substituents shifts the lambda max towards longer wavelength. In case of pi-pi star transition, if there is a conjugation is being extended in the molecule, then, or you have conjugated double bonds, and or you have any alkyl substituents added to the molecule, then you will see the wavelength of absorption shifting towards longer wavelength. This is called bathochromic shift. This also we'll see in subsequent slides. This is called the K band. With solvent polarity, it works the opposite way as n-pi star. So actually the pi-pi star transition with increase in solvent polarity would undergo a bathochromic shift. So these are electronic energy levels and transitions. Here you have the transition column. This is the region of electronic spectra, and these are some examples. So for us, most important is pi-pi star. This takes place in the ultraviolet region, and this is shown, say, by saturated aldehydes at 180 nanometers. One example this is, it is shown by many more compounds. Anything which has unsaturation. Aldehydes have C double bond over CH. That group is their aldehydic group, and that's why it will show in the pi-pi star transition. N-pi star transitions are shown in the near ultraviolet and the visible region. So at longer wavelengths compared to pi-pi star, involving lesser energy compared to pi-pi star. Example is acetone. It has O. So acetone at 277 nanometer, you can see the longer wavelength, and nitroso-T-butane at 665 nanometer. These two, N sigma star, rarely seen. It's seen in the far ultraviolet, sometimes in near ultraviolet. Okay, and that is from 180 to 380, very rarely. For example, acetone at 190 nanometers. So acetone has two. It shows N sigma star. It also shows N pi star transition. So there will be two peaks. Now, methylamine at 213 nanometer. So sometimes it goes into the ultraviolet region, depends upon the molecule and its own set of energy states. Sigma sigma star is always in vacuum ultraviolet, C14 at 125 nanometer. And that's why we cannot observe these with the ultraviolet and visible regions we use in spectroscopic studies. So now we come to some definitions of certain terms that are widely used in spectroscopy. So you should know the definitions. This could be asked as short questions. So what's a chromophore? Chromophore is an isolated functional group, not in conjunction with any other group, and exhibiting absorption of a characteristic nature in the UV or visible region. So a chromophore refers to a functional group by itself. It will exhibit a characteristic absorption in UV or visible region without being connected to any other group. Also, it should be capable of absorbing. So this is the group. The chromophore is the group that is responsible for absorption in a molecule, responsible for UV visible absorption in a molecule. Some examples of chromophores include the carbonyl group C double bond O or the C double bond C group, nitro group, azo group, phenyl group, etc. So all these groups are chromophores. If they are present in a molecule, then the molecule definitely will absorb UV visible radiation. The other type of group is the auxochrome. See the difference? This is chromophore, this is auxochrome. These are groups that do not in themselves show selective absorption above 200 nanometer, but when attached to a chromophore, usually cause a shift in the absorption to a longer wavelength or an increased intensity of absorption peak. So auxochrome, these are groups. By themselves, they will not show any absorption in the UV visible region above 200 nanometer. But when they are attached to a chromophore, that is, you have a chromophore and an auxochrome very closely bonded to the chromophore, then it will show an effect on the chromophoric absorption. What kind of effect? It may cause a shift in the absorption to a longer wavelength. It may also cause an increased intensity of absorption. So these are the effects shown by auxochromes, which are very closely placed to a chromophore. Otherwise, by themselves, if they are present, then they will not show any absorption in the UV visible region. Examples of auxochromes are OH, NH2, SH, some of the halogens, etc. So here you have the various chromophores. I have put this for information. You need not remember this. One or two to cite examples is enough. So carbonyl group, I already told you about this. These are some of the chromophoric structures. I have added some more extra ones. So carbonyl group, it will show absorption at 280. The azo group at 262. Nitro group at 270. Benzene or the phenyl nucleus at 261. Similarly, you have the nitrite group 230. Then you have the thioketone at 330. You have the conjugated dienes, two double bonds separated by one single double bond. That is 233. Conjugated trienes, three double bonds, each separated from the other by one single bond. 268. Conjugated tetraenes, that is four double bonds that are in conjugation at 315. You can see that the wavelength of absorption goes on increasing as the conjugation is increasing. It's what I told earlier. As the conjugation increases, the wavelength of absorption shifts to longer wavelengths. This happens in pi star transitions. Chromophore plus auxochrome gives a newer chromophore, and that's why it absorbs at a slightly different wavelength and with a different intensity of absorption. Oxochrome is a color enhancing group. That's why the intensity is increasing. The effect is due to its ability. Why is it a color enhancing group? The effect is due to its ability to extend the conjugation of a chromophore by sharing the non-bonding electrons. The new chromophore that is formed has different absorption maximum and extinction coefficient. Now say for example benzene. It absorbs one of its peaks is observed at 255 nanometer with an epsilon max of 203. Aniline, if you see the same peak, aniline, which is benzene with an added amino group. So aniline absorbs at 280 nanometer, that is longer to 255, with an epsilon max much greater than what is shown by benzene. So 1430. So the oxochrome group is NH2. Benzene is the chromophore and oxochrome NH2 is added to it. It gives aniline, which shows that the absorption peak is shifted to longer wavelength with an increased intensity as evidenced by the increased epsilon max value. So some examples are these which I told you. These are all oxochromes. So now I also mentioned about some shifts. So what are these shifts? You have bathochromic shift, hypsochromic shift, hyperchromic shift, and hypochromic shift. So bathochromic shift is a shift in absorption to a longer wavelength or lower wave number. This happens when an oxochrome attaches to a chromophore. Same thing, benzene ring, you attach OH, that is you get phenol. You will see that the peak will shift to longer wavelength. Hypsochromic shift, HYPSO, hypsochromic shift is a blue shift, shift in absorption to shorter wavelength or greater energy or higher wave number. Hyperchromic shift is increase in intensity of an absorption peak, and hypochromic shift is decrease in intensity of an absorption peak. So